No. Oh, his leg came off. That's gotta hurt. All right. So I want to show you. I don't have the actual physical thing with me, but this is kind of nice. So it's this shape, right? And when you open it, there you go. It's actually a ellipsoid. It's sort of like my thing. Open it up a little bit. You got Pac-Man. Sorry. And now, the idea is, let me go over to this other one. Is everybody cool with just that bit by itself? What we're doing is we're creating solids by revolving a 2D image, which, you know, when you go to construct or create something, that might be one way to create it. So it has these symmetries that you want. You do it in XY plane, and then you construct it so that when you rotate it, it becomes what you want, right? So we're trying to figure out, can I get the volume of the resultant rotation using the integrals that we understand? So if you get to Calc 3, you will discuss things called double and triple integrals that you can use in higher level, like three-dimensional problems. This is not going to need that. We're not going to need that at all. The idea of how this works is too nice to believe. Let me show you another picture. So here I've got, let me see if I can't. So this is this is an equation of a sphere up here. X squared plus y squared plus z squared equals 1. It's kind of like the equivalent of r squared equals x squared plus y squared in 2D. So I'm trying to approximate the volume of the sphere using these disks. And just like with rectangles, the approximation becomes better the more of the shapes that I use. So if I increase, so here's the volume, there's the actual volume. So we can come out of here a little bit. No, you won't let me come out? You dork. All right. Here's the actual volume down here in the corner. Here's the approximate volume. If I increase the number of disks used, the approximating volume becomes closer and closer and closer to the actual volume. Just like with rectangles, right? Now, there's a beautiful connection between rectangles and creating these volumes that we're going to see. There's two main approaches to doing these, and that's what I was telling you about the other day about when do I use which approach. So there are definitive things you can look at to tell you when to use which approach. The approaches are called washers, disks. That looks like it would be a washer kind of idea. See, the pieces would look like washers, right? Or disks, really, in this case. Washer would be if there's a hollow part down the middle. Then that would be a washer that I'm working with. And then the other one is called shells. Cylindrical shells. So if you imagine a rectangle and you rotate it, you've made this shell shape. So they're both, somehow those are going to directly relate to how we set an integral up. And depending on which way we're rotating and how we can write the function will tell me which approach to use. Sometimes one approach is possible and the other one's impossible. Sometimes one approach is easier while the other approach works. It's just harder. Okay. Let's see if I have one more. Do it. There we go. So here's a typical example. There's y equals square root of x. So part of our work is always going to be drawing out just in 2D the shape we're starting with before we rotate it. You don't have to be able to draw 3D at all. You don't really have to do it at all. I'll show you the important parts to get. You can just get what you need from this image. So the whole idea here is we're gonna take this from 0 to 1, the y equals square root of x. We're going to take this area and we're going to rotate it. Should be around the x-axis. Where does it say that? Let's find out what it is. you see that? Now, part of your brain is going to tell you, well, then the equation for this has got to look disgusting. But I actually never go into 3D with my integration that I'm going to do. Because what I do is, do you see that red area? That's kind of like the stand-in for a rectangle. Except now it's of course, what shape is that? Circle. And along which axis is that traveling? So if I move along obviously the x-axis, what changes about that slice? What changes about that circle? The radius, right? Or the height. I like it. All right, I like it. So I want you to really, this is really kind of nifty. So how would I get the volume of this shape then? I would just take all the possible disks, all these disks, areas, and add them up. I like it. Now how many possible disks are there? Well, how many numbers are there between 0 and 2 pi? Or what is it, 0 to 1 here? Oh, I see. This is just to rotate the region. Whee! How many numbers are between 0 and 1? Infinite number. For every single one of them, there's another disk. So, of course, we have to do continuous summation, which is what integration is. Does that make sense to say that? So limit is then goes to infinity of a sum I equals 1 to n. And that just becomes just continuous summation. You don't skip anything. You're not adding this rectangle to this rectangle. You're adding this infinitesimal sliver to this infinitesimal sliver. I like it. So this guy, let's figure this guy out. Let's look at this guy. Since we got the visual up there, let's figure out what the hell this would look like. So what I'm doing is I am working with this function, the square root of x, from 0 to 1 it looks like. Yep. Rotating that around, you do not have to draw that 3D. If I rotate it around the x-axis, that means what I'm going to do to get the total volume is I'm going to add up all the cross-sectional areas of those circles. I'm going to add all those up all the way through, from 0 to 1. So for some position x, what is the area of that slice? What is the radius of that slice? Or like Brian said earlier, the height of it really, to be honest, but then we realize it's a radius once I rotate it. But right now it's a height. So what's the height there? Yeah, which is square root of x. So the radius in this case is going to be the square root of x. Just like the height of a rectangle was f of x. Exact same thing here. Why am I now looking at it as a height? Because I'm going to rotate it, it becomes a circle. So then we call it a radius. But right now I can think of it, well, it's just like a height. Just like my little rectangle. Now if I take a rectangle and I rotate it through, doesn't that become a disc? Like almost like like a weight at a gym. Right? You guys with me? A little bit. That thickness is dx. What is the area of this representative circle? What's the area? Well, what's the area of a circle? I'll start there. Pi r squared. So in this case, what's the radius? Square root of x. So in this case, the area of all of those, of any cross-sectional slice circle is pi x. Just because the square case. So whatever that function was, I can make it x squared, I can make it whatever the shit I want to, and then rotate just like we're doing, that's going to be the radius. Now just to say this right now, we're not going to do this quite yet in the work, but why is the radius exactly equal to this? Why do I not have to adjust it at all? Because I'm rotating around the x-axis. What if I rotated around the x equals -1 line? Maybe I can make the scale the same. That'd be nice. What's the radius then?
X plus 1.
Square root of x plus 1. Right? We're going to get there. To be honest, we would have an inner radius and an outer radius and so forth, but we're going to worry about that later. But just to show you that you got to be careful when they say rotate it around something that's not a primary axis. I'm going to have to adjust by radius then. The only reason this radius was so easy is because it's going around the x-axis. That's exactly the distance away from the x-axis, isn't it? If I do it around some other thing, oh shit, now my radius got bigger or smaller depending on where that axis of revolution is.
So is the point X, would that be like the average height?
No. This is just a representative X somewhere in this whole thing. So I'm going to have to add up all of them. I just picked a random spot to write what any circle's area would be. Now, it's not just the circle though. Remember, it's this rectangle. What's the width of the rectangle? Dx. Beautiful. So what I've really got, this is why we call the method washers and discs, because what I really have here is not just a circle, it's a disc. It's got a thickness. So what's the volume of the disc? It's going to be the area of the circle times the thickness. So it's just going to be pi x dx. And this is actually, let me be a lot more careful with this. This is actually a little volume element, dV. So I'm going to add up all of my volume elements, and that's going to end up giving me the entire volume.
Why is dx? You said dx is what?
Is the width of one of these rectangles. I like that. So that's why it's called the disc method. This is not just a circle. I kind of wanted to start there to make you guys realize it does involve circles, but see how this has, I wish I could zoom in. See how this has a thickness to it. The thickness is dx. Just like the width of our rectangles start off as delta x, but that becomes what in the limit? Dx. Same thing's happening here. I like it. So then all I have to do to get the total volume is to integrate, to add up all these little slices of volume. If I add them all up, I'll get the total volume. Well, how do I add up an infinite amount of things? I use an integral. From what to what in this case? So I get the volume, and I don't really need that. I get the volume equals, and now what would happen here? How do you integrate this? Don't let pi freak you out, it's just a constant. Pi x squared over 2, evaluated from 0 to 1. So I get pi over 2. Plug 1 in, you get pi over 2. You plug a 0, you get 0. Real quick, just to get a feel for, there's no good way to show you, and this is the first thing that popped in my mind. How do I check this? Well, I can approximate this as maybe half of a sphere of radius 1. You guys see that? Why isn't it quite right? Because it's not really the curvature of a sphere, but let's see what the volume of a sphere of radius 1 would be. Well, what would that be? Volume of a sphere is 4/3 pi r cubed. If I had radius 1, it would be 4/3 pi. And I want half of that. I don't know if you guys are really with me. If I say, doesn't this look like, if I rotate it, doesn't that look like half of a ball? Not exactly right. This is not the right curvature, but I just want a rough guess. I just want to see an estimate. And what's 1/2 of 4/3? 2/3 pi, which is really damn close to my pi over 2, to be honest. It's a really rough estimate. So the idea is instead of, I really want to make this distinction. What did we do with integration first? We had a function, and we would, if I integrate from 0 to 1, the function, if I just do this, it's going to add up all these little rectangles areas to give me the whole area. So really what we were doing was this. Integral area elements gives me the total area. If I add up all the little areas of those rectangles, I'm going to get the entire area. So what I'm doing now is every rectangle that would have been there before, I'm now tying it to a disk and realizing that it doesn't change the math directly, really. It's the same idea, except now instead of adding up a bunch of areas of rectangles, I'm going to add up a bunch of volumes of disks as I move through. That's why visually it does become three-dimensional, but my integral didn't become like three-dimensional somehow, right? Do you guys does that look like, if you saw that, does that look different from any integral we've done before? This is the same thing, but this represents the volume of that three-dimensional object. This is what I was saying earlier. And I've reorganized the volume of that into an integral I know how to do using this awesome idea of just adding the volumes of all these little cross sections. Yes? No, this is 6-2. Yes, 6-2. Okay. So the washer method works, the disk method works really well when, how do I say this? When you're, see how this is a function of x. This is y is a function of x, and I'm rotating around the x-axis. Okay, I'll lock it. So let's try something a little different. I'm still using washers and disks. Oh, let me do this for you guys. Let's kind of write what we've done in general, so we have sort of just a format, an algorithm to use, like a formula to use. So in general, given some generate solid, rotate around the x-axis, let's say, just like we just did. Then the volume will equal the integral of pi times f of x squared. That's pi times the radius squared. And that's the disk method. Let me see if I can't. Now I want to do this. Oh, and they do this exact same problem. This is kind of nifty. Page 441 at the top. You can kind of see better visuals of what we're doing. Thankfully, they get the same answer. It's always nice. Yes?
So that was the disk, right?
Yeah, disk method. To be honest, I wish we would not have given the other thing a different name. Here's what the other method is. It's called a washer because washers have holes in the middle. So it's like you want to bore a hole through something. Or let's try to do this. Let me redraw this. And we're going to do, like I was saying earlier, we're going to rotate this around the x equals -1 line and see how that affects things. Is that going to be too gross? Well, we'll find out. So let's see, we have our y equals square root of x. I want to rotate it around x equals -1. So here's my, and we're going from 0 to 1 still. So now I'm going to rotate it around this line. This is going to be my axis of rotation now. So, say again, sorry? rotate around, x equals, I'm sorry, thanks. I don't want to do that for you. Y equals -1. There's a part of the method of telling which way is the best way is if you're parallel to a certain axis, you do it a certain way. So this is going to be parallel to the x-axis. My y is a function of x. That's telling me to do it the Washer method. Now, what I just said doesn't make the most sense yet because I got to tell you how the other method works, and then you can play them off each other. You can see when to do which one. If I rotate this thing the way it is now, this area right here, this area, do you see how there's going to be a giant open hole in the middle, right? So maybe it's like a bundt. Have you guys ever seen a bundt cake pan where they have, they have the hole in the middle and then you with me? Okay. Some of you guys? All right. Never? Sure. So from above, it looks like this. It's got these little, this goes straight through. So your cake comes out with this hole down the center. And yeah, I think it's bundt cake. All right. Yes. Okay. Good old. Like, you didn't get used enough. Let's put it in there and make it silent. So if I rotate this, let me see if I can do my disgusting. Oh, that's a little too much, Jeff. All right. So I rotate this. So it's going to be there. So you got to imagine this is 3D though, so it's not going to fall apart. It's just going to have a hole down the center. This is going to be filled in all the way around. Stop here for a second. Again, you don't have to actually draw everything I just did. You really just have to work with it here. You just have to be able to, because you can get everything you need from just the 2D part.
Is it saying y equals -1 is the center of the rotation?
Yes, exactly.
So wouldn't there be a space below?
Yes, there should be. I knew there was something that looked a little freaky. So this is the center, so it should repeat this down here. I like that. So I was big enough. Sure. So now this is going to be the filled in part. Let me see if I can do this right. Yeah, this is that much away, this is that much away. So then this is going to be like that. That looks a little bit better. Oh, it looks disgusting, but too bad. So that's the filled in part. Okay, so this whole middle is going to be like bored out. So it's like a bundt cake with a giant hole in the middle, but well. Okay, now again, thankfully you don't have to draw all of this. Really all you need is represent the rotation axis. The reason they call it washer and the reason they make it sound like it's a whole different thing is this isn't filled in. So if I just say that's my radius right there, what would this be? What would this radius be? We already talked about this earlier. The radius is going to be square root of x plus 1. I like it. So it's pretty much always the outer thing minus this. That becomes plus 1. But if I actually do everything, all the work we just did, I'm going to get something as if it was solid all the way through. So don't I have to subtract this guy? So that's why you actually have an outer radius, and then you have an inner radius. Now, of course, the inner radius is just going to be 1. So officially, the formula for something with a hollow center is going to be the integral from whatever to whatever, pi times r outer squared minus r inner squared. Do you see how that's the area, and then of course times dx. So that's going to be, this is the volume of the outer disk, and this is subtracting the volume that's going to be taken out. That's not going to actually be, there's just going to be a hole. So it is exactly like boring out the center of the shape. So how do I fill this in? Well, it's still going to be, so here's why I don't need all this. It's still going to be from 0 to 1. I know that from the original picture. That's what my x is doing, 0 to 1. Pi. I can get my outer and inner radius just from this 2D picture. I don't need 3D at all. The outer radius is square root of x plus 1. And the inner radius was just 1. Of course, I hope this makes sense. If I push this further out, it seems like the volume is going to automatically be a lot less than the original problem we did, but the further I make this go, the more stuff there is as you rotate it, right? So you have those two things competing. So here you just got to, I can take the pi out. Got to FOIL this sucker out, so I get x plus 2 rad x. Let's write that as x to the 1/2. There we go. Plus 1 minus 1. That's nice. So this is why they call this the washer method. But you see how it's just the disk method twice? It's just an outer disk and then subtract the inner disk to make the middle hollow. And now this shouldn't be too crazy. How do you integrate that? X squared over 2 plus 2x to the, at least some space there. This goes to 3/2, and then in front of it you put 2/3. I like it. It's times. Yeah, there. And evaluate it between 0 and 1. So again, thankfully 0 does 0 everybody out. I can forget them. When I put a 1 in there, I get pi over 2. That's interesting. Plus 4/3 pi. So what won out here was I did lose some in the middle, but I gained a lot more because I went further away. I got a lot more to rotate around. I picked up a lot more volume that way. So you have this giant cake with this huge hole in the middle if you use that pan we just made. I really desperately want you guys to see how this idea is not very far away from what we were doing. We were adding areas of rectangles to get a total area. Now we're adding volumes of disks to get a total volume. So it really shouldn't change the math much, and it doesn't. The only real change is I've got to first figure out what is the area, what's the volume of these disks that I'm adding up, right? Whereas before it only depended on the height of the rectangles I was using. Yes?
Do you add those up that bad? The pi over 2 plus 4 pi.
Oh, yeah. Since these are, like terms, you can, so 3 pi plus 8 pi, 11 pi over 6. I like it. So almost 2 pi. I like it. All right. Let's do this. I'm going to lay out the shell method. There's a lot more to this method, but it involves details like what if I rotated around the y-axis instead, stuff like that. Right? Now let's look at that. Maybe that'll lead into this next method. What if I had the same setup, the same area I was going to work with, but I had to rotate it around? See what you do. You don't do much. So I have the same y equals square root of x, but I'm going to rotate it around the y-axis. So I've got this region still. But now I'm going to rotate it around the y-axis. So here, remember, I kind of did this quickly, but what something that becomes very important is to draw a representative rectangle for what we're working with. See how here the rectangles would march along the x-axis because we're rotating along something parallel to the x-axis. So that works beautifully with disk method. If I want to use disk method here, what axis am I going to march along now? The y-axis. So my rectangles would have to look like this. So then when I rotate, I do get my disks again, don't I? If I rotate like that. So here I was rotating around the x-axis. Do you see how my rectangle is perpendicular to the x-axis? So for disk method, you want your rectangles to be perpendicular to the thing you are rotating around. That way they actually create disks when you rotate them. If I had straight up and down and I rotate, it doesn't create a disk, it actually creates a shell. That's the shell method. If I had a rectangle here and I rotate it around, I get a shell. I don't get a thin disk, I get this big ass shell, right? And they have their own formulas for their volumes. That's going to be the next method. But if I want to try to still use disk, this is what I've got to use. My y is a function of x though. Now I want, what's going to be the controlling variable? Like we just figured out, the y is. So I need to be able to write my function in terms of y now. So of course in this case we have a nice function we can. What is that in terms of y instead of x? Just solve for x.
Y squared.
Yeah. So that's this. Let's see, he's already got this here, hopefully.
Is that 6-3, washer method?
Washers are 6'2", shells are 6'3". Yeah. Yeah, washers are disks, just subtracting 2 disks, so they're together. So now, if I want to use disk method, I have got to have my little d, in this case it's going to be dy now, but my little rectangles have to be perpendicular to that so that when I rotate, I do get my little disks. So we're with that. So it was easy with the x stuff. We're used to x stuff. So we've been doing the whole semester. Now I'm going to suddenly change everything up on you. Now we're doing everything dy. Oh shit. That's why I need x as a function of y. Because if I have an integral dy, I have to put into it a function of y. Now, hope to God you guys are to the point where you realize the x-axis being here, the y-axis being here is completely arbitrary. In fact, their names are completely arbitrary. If I can integrate along the x-axis, why the shit can't I integrate along the y-axis? So, like, if the area of this is 1, well, then the area of this, assuming it could also be 1. I should be able to... Okay. So, let's not go there yet. What's my, what method am I going to use to be more specific? I'm going to have kind of an empty space in the middle. It's going to be a remarkably strange bowl, right? This is like a high-end restaurant where you're like, I'm not sure what to do with this. If I rotate this thing, can you guys see it's going to have this big open space in the middle? Right? That's not too bad for me, to be honest, but still shit, but oh well. It's going to have this big open space in the middle, is it not? It's going to be this weird-ass bowl with like these straight up and down sides, but oh well. That's what it's going to look like. And again, you don't have to actually be able to draw that, but so what am I going to use? I have to have an inner radius and an outer radius, right? What's that inner radius going to be? It starts at 0 and goes to what? Y squared. So the inner radius is y squared. And look how that makes sense. At 0, there should be no radius. It's right there. And sure enough, when y is 0, you get 0. At 1, the radius should be 1. And when you plug 1 in for y squared, you get 1. So this is exactly the same as earlier when we had this and we said, what's the radius here? It was just going to be this height in terms of x. Well, now I'm talking about in terms of y. That's why I had to make that function in terms of y. So that inner radius is y squared. What's the outer radius? This is too nice to believe. And real quick, why does the inner radius have to be dependent on y? Because if you move up, doesn't the inner radius change as you move? Depending on what y is, it goes further and further out. The outer radius, though, is just always 1. That kicks ass. I like this. We're going to redo this problem with shells and show you how Shell's method will make this a lot easier than this. It's gross. All right, so now I can set my problem up. So in general, it's going to be integral from a to b, pi times r outer squared minus r inner squared. Now it's dy, just because of the orientation of the problem. But now I just plug my stuff in there. I get integral from, now what's y doing? Remember, that's the controller. That's why this is a big time deal, is if you put that dy down, it reminds you everything's about y. Now in this case, you can't go wrong because y is going from freaking 0. But in general, it could be doing very different things depending on the function. So y goes from 0 to 1. Outer radius is 1. Inner radius is y squared. You got to square that. That's another mistake. Your radius inner is y squared, and you got to square it. And then here you get, let's see, we get pi. Let me take a pi out. I get 1 minus y to the 4th. Y's and 4's are my downfall for sure. So I get pi times, what's the integral of 1 dy? Y. And integral of y 4 dy is y fifth over 5. Get out of there, s. Become a 5. Sure. And then when I evaluate that from 0 to 1, again, it's nice for the 0. So I end up with pi minus pi over 5. So I got 4 pi over 5. So let me give you this. I'm going to give you this now as we step into shells, because shells is nice to have a clear picture to look at instead of what I would be able to draw. Have a computer draw it for me. As promised, this is my most colorful handout ever. Well, let me see if I can do this. So look at the very first little paragraph. You can look at the pictures. There's discs, there's washers, which is really just 2 discs. The inner disc is subtracted from the outer disc volume. There's the first thing we came up with earlier, right? dV, the little volume element, is pi f of x squared. Then we did a washer one with the outer radius, inner radius. That's the one we just did. Notice here's where I try to break this down for you. In the disk washer method, it is dx when revolving around an axis parallel to the x-axis. And it's dy when you revolve around the y-axis. So right here, we're revolving around the y-axis. I've got to use dy if I want to use washer method. So when would I not want to use washer method or disk method is if I have a function I cannot solve for x easily or at all. You with me? So if my function had been, open up. If my function had been y equals x squared minus 3x plus 11, can you solve that for x? Yeah, you can, but you don't want to. You'd have to use quadratic in some of the strangest forms. To be honest, it works more than you think, but there's no way in shit hell that I want to solve this for x. Are you with me? Even if you can, theoretically, I don't want to. So you start to see how you figure out which method to use. If you want to use the disk method, when you're revolving around the y-axis or something parallel to the y-axis, it must be dy. Because then that's the axis you're going to march along. That's what I'm trying to tell you. That's the axis that's going to control everything. You have to march along that. Shell's method does that the other way. So if I have a function I cannot solve for x, and I'm rotating around something parallel to the y-axis, I don't want to use freaking disk method. I can't. I have to use Shell's method. It's the one that kind of turns my rectangle the other way. So we're going to do this problem again using shell method. I have got to get the same answer. So obviously there are some that you can use both methods for. So let's see how this works. First off, I want to show you, just like we did earlier, this is much easier. The volume of a disk is very easy. Now we got to figure out the volume of a shell. And really all it boils down to is, here's a cylinder. So a cylindrical shell is just one that's got this hole down the middle of it. So we've got everything labeled in there for you. So I'm not sure if this came up in this class, I can't remember, but if you take like the label of a Campbell soup can off, or your favorite whatever can, and you open it up, you've just created what shape? Rectangle. And of course, if I did that, if I cut this down and I open it, boom, and there it is. This is the height. This would be what? This came from the circumference. I love it. So 2 pi r. So what is the area of that? 2 pi r h. So it's really boiling down to shifting the areas I'm working with into a rectangle, right? So 2 pi r h. So what is the volume of the disk? Well, what is this going to be? This is going to be dx. To start with, it could be dy, depending on which way we want to orient things. So that's why up here it's got 2 pi r h dx. Right underneath that shell. Is everybody with that right there, by itself? Now, in general, for really nice problems, that radius is going to be just x. This is all in terms of, I would just change all my x's into y's if I had to do it that way. Okay. So the radius, just like before, so let me draw this picture again. And as we start to do the problem, you can see how it all relates to this. So if I draw this picture one more time, we've studied the hell out of this poor little area here. So if I use shells, here's the idea. If I rotate around the y-axis, this would be disks, because then if I rotate them, I get these long, so it's skinny this way, right? Shells would be this, and I rotate it, and I end up with that shape I had earlier, which I wish I had kept here. There you go, Jeff. Not bad, not horrible. Just disgusting. All right. So if I rotate that, do you see how it becomes that shape? Is that cool? If I rotate a rectangle, it's going to become that shape. Yes?
From like what point? Like from
Oh, so in this case, I'm assuming I'm going around the y-axis, just like we did over there. Right.
Well, like where do you know where dx is?
Oh, well, dx is just going to be there. Same way as before. What's the height of this going to be?
Like, how did you find where to put that rectangle? Like, you just put it in the middle?
Oh, yeah. I normally put it in the middle so I have enough room, but it's just a representative rectangle. I could have made it this one. I could have made it the one on either end. It's just a representative rectangle somewhere. So every rectangle will have these dimensions. It's just going to change depending on where I am. I like it. Good point, though. There's no reason I put it where I did. Since I normally put it in the middle, just so I have room to work. What's the height of this? Yeah, in general, it's going to be f of x. In this case, it's square root of x. So in general, the height is going to be f of x. Of course, everything kind of shifts as I'm doing it around the other axis. We're just doing an overview right now. We are going to get a lot more detailed problems. Good. Okay, all right. So now I am, so I've got my y equals square root of x. I decided I didn't want to solve for x. I'm going to do shell method. Shell method says if you're rotating around the y-axis, then you can put your rectangles perpendicular to the x-axis. That's what it allows. So this works both ways because it's such a simple function, but there obviously will be functions that you cannot solve. You're forced to do a certain method. So if I rotate this, you start to see that shape develop. Right? This is really not bad for me at all. Right? You're like, yeah, for you, Jeff, that's pretty good. You work now. So now, this little element is going to, so this is a little volume element. So now I just want to do this. Now I want to, my volume is going to be the integral 2 pi x. What's f of x? Well, that's just square root of x dx. And going from what to what? It's all about x now, so you go from 0 to 1. In this problem, you couldn't go wrong in whichever way you looked at it, but in general, you look here, and that tells you what to look at for your limits. So then you get, what do you get? So I can take the 2 pi out. What is x times square root of x? What's a better way to write that? Yeah, x times x to the 1/2 becomes x to the 3/2. There is no product rule for integration. Don't integrate this times the integral of that. That ain't even how differentiation works. And integration should be harder every time. So there is no product rule for integration. There is integrations to answer the product rule, which you'll learn in Math 280 if you take that. If you don't, too bad. We use a different pen, or we'll do the rest. So let's see, we get 2 pi, what's the integral of this? X to the 5 halves, and what's in front now? 2/5. So I get 4/5 pi, and this is evaluated from 0 to 1. So I get 4/5 pi, right? Is that cool? Times 1 is 4/5 pi. What do we get the other way? Four-fifths pi, right? So we did it with disks, and we got 4 pi over 5. We did it with shells, and we got 4 pi over 5. And to be honest, this problem came out to be even in terms of amount of work. Because it's a relatively simple function, so it could work both ways. It can be turned around. It's nice. So I really try to make it straight and to the point in terms of knowing which way to use. In the disk method, you've got to make, if you're revolving around an axis parallel to the x-axis, it has to be dx. Which means your function has to be in terms of x. And if it's, so vice versa. If it's rotating around something parallel to the y-axis, there has to be a dy to use a disk method, which means your function has to be in terms of y. So one quick determiner about that is, okay, which one has it got to be, dx or dy, and then can I put my function in that form? If the answer is no, then you use shells. Whatever one will not work for, the other one has to. They perfectly complement each other. In fact, they over-complement each other because sometimes either one works. Maybe. I think we're just getting into this. Now look at the shell method. The rectangles are located on an axis perpendicular to. So here I was rotating around the y-axis, so I'm going to locate my rectangles on the x-axis. Bang. And then I give you the therefore that I just talked about. So let me see if you guys can do this. Look at the very bottom. There's a problem. It's all computer drawn for you. Thank God, Jeff drawn. Can you try to set that up? Well, first step. Just think about, is one method better than the other one? Just think about that.